problem 23 from the review paper. In this problem, a satellite is in a circular orbit about the Earth. The period of the satellite is given at 1.2 times 10 to the 4th seconds. What is the speed at which the satellite travels? Now we've got our picture drawn. Our satellite's orbit is here in green, the overall radius there in pink. The time that it takes to go around once is given at 1.2 times 10 to the 4th seconds, and the mass of the Earth is written on the board in the class, and I told you to write that down, so you should have that value. From here, as always with any object that's going around anything else, we know it's uniform circular motion, so there is a centripetal force. And the centripetal force in this problem is the force of gravity, because we're talking about an object that's going about the Earth in space, so Earth's gravity is what's holding it there. From here, we can expand our equations. The centripetal force equation that we would want to use is probably the one with the time in it, because we have the time, so it makes sense to use that version of centripetal force. So it would be the mass of the satellite times 4 pi squared r divided by the period squared. And for gravity out in space, we have to use Newton's law of universal gravitation, which is big G, mass of the satellite, mass of the Earth, all divided by the distance between them squared. Now we do a little bit of algebra. We know that the mass of the satellite is what we're talking about with the centripetal force, and we have mass of the satellite on the other side of the equation, so those can cancel out. You cannot cancel this r and this r. They are on two different sides of the fraction bar. They do not cancel. So one's in the numerator, one's in the denominator. They don't work like that. You can't do that algebraically. It is wrong. So what we are going to do is actually solve this for r. When in doubt, we're going to solve for some stuff. And you might be saying, this question is asking for velocity. That's true. And the equation for velocity is 2 pi r over t. We have t. The only thing we're missing is r. We just need that radius. If we can find the radius of the orbit, we can very easily solve for speed. That's why we have our centripetal force and gravity equations set up. If we can solve for r, we get it and plug right back in here in order to find the velocity. So let's do that now. We're going to rearrange this equation for r. I think it's easiest to get stuff out of fractions. Fractions tend to become problematic. So I'm going to multiply the r squared on the right side up to the left. And that's going to give me 4 pi squared. R times r squared here becomes r cubed. And what I'm going to do on this left side, I'm going to multiply the time squared up to the right. So it will no longer be on the left side, it'll be in the numerator on the right side. So it'll leave me with g, mass of the Earth, times the time squared. Now we have to get rid of the 4 pi squared. Since it's being multiplied on the left side, we're going to divide it. So I'm left with r cubed equals the gravitational constant times the mass of the Earth times the period squared, all divided by 4 pi squared. Now we don't want r cubed, we want actual r, so we have to do a cube root. You might not have seen that too often in your math classes, but it works just like a square root, except it's a cube root. Very similar. Calculator has the ability to do it for you. So what that looks like is r equals, put a little 3 here, let us know it's a cube root, g, mass of the Earth, multiplied by the period squared, all divided by 4 pi squared. From here we can plug in the numbers. These numbers tend to be rather long, so I'm going to go to a new slide in order to write the numbers in because we don't have enough room left on this slide. So it was r equals, first we had big G, which was 6.67 times 10 to the negative 11 meters squared per kilogram squared. Then we had the mass of the Earth it was being multiplied by, which was 5.972 times 10 to the 24th kilograms. And that was being multiplied by the period squared, which was 1.2 times 10 to the 4th seconds, and that gets squared. All of that was being divided by 4 pi squared, and that was all under a big cube root. If you plug all of that into your calculator correctly, you should get that the radius is 1.133 times 10 to the 7th meters. So that is the orbital radius of our satellite. Now, as I said, finding velocity should be very simple from here, since velocity is just 2 pi r over the period t. So I can plug in my numbers. I get 2 pi times 1.133 times 10 to the 7th meters. It's all over the period, which was given in the problem at 1.2 times 10 to the 4th seconds. If I plug all of that into my calculator, I get the answer 5,932 meters per second. You might think that seems rather large, but that's actually a fairly standard speed for a satellite that would be in a very low Earth orbit. And that is how we do problem number 23 from the review paper.